I realized after I had already posted that last video that there was one more pair of parametric equations that we had used to practice eliminating the parameter. So I've put those up here as a so-called point in Desmos as well. There's my x-coordinate. It depends and is defined by t. And there's my y-coordinate. So this pair of parametric equations originally said x equals 5 times the sine of t minus 3 and y equals 5 times the cosine of t minus 4. I've entered them here as though they were coordinates in a pair. When I click on the graph, this is what I get. So this is the record of that pair of parametric equations where t varies between 0 and 1. Now I'm going to leave it varying between 0 and 1 for the moment because I want to show you something. Here's one of the benefits of using parametric equations. I have a second copy of my parametric equations here, but instead of t, I have a. What that's going to do is allow me to track a point along the curve that the parametric equations define. When I animate this point, you'll be able to see that it's tracking along that curve. But importantly, you can see that it starts when t equals 0. In this case, it's a equals 0, but it's the same curve. So when t equals 0, it starts here, and it travels in this direction. That's an important piece of information that we're missing if we don't have parametric equations, if we just graph the curve. Now, the other thing that I've done here is I've left a to be defined as, and t to be defined as only going between 0 and 1. And that's because I wanted to ask you if you could figure out, if you could guess what the whole curve might look like. Let me redo that. I'm zoom out a little bit here. That might be too much. So what do you think this is? Now, it may seem obvious, but it's interesting to me that once I know what this thing looks like, I'm going to be able to look back at the equation and tell something about the curve just from the equation. In the same way as we could do that with polar coordinates. So what I'm going to do now is I'm going to let t go to first 2. And you can see there's more of the curve there now than there was before. And then 3. And then 4. And yes, it is in fact a circle. So if I let it go to 6, the circle doesn't quite get complete. And that's because it's based on sine and cosine. And sine and cosine both have periods of 2 pi. So I need to change my domain as going from 0 to 2 pi in order to get the full circle. Now, even though this is, let's go back to 6 for a minute. Let me show you something. This second version of the equation was based on a. I'm going to let now a go from 0 to 6. And when I animate, you can see that it starts here and it goes around. And then I have it set so that it starts over again. Might actually be a little bit, I think it's a little bit too big. Let's change it to 5. Because I want you to see that there's a jump. And the reason there's a jump is that I have the loop repeating, not starting. It doesn't go from the beginning to the end and then reverse, which is what would happen if I had that selected. Let me show you what I mean by that. Here it's going to get to the end and then go back the other way. I didn't want that. I wanted it to start at the beginning again each time. So it gets to where t equals 5 in this case, and then it jumps and starts back at t equals 0. If I change this domain so that it goes all the way to 2 pi, then I get a complete circle. I'll need to change that here as well. 2 pi. But now when I hit play, you're not going to be able to see a jump because it's starting back at t equals 0 each time. In fact, you can't even see where 0 is. To get that, I have to stop the animation and put the point at t equals 0. Anyway, so I wanted to include that, but I forgot to include it in the previous video. So here's a separate video for that. I'm also, though, going to turn on the minor grid lines. And in fact, I think I will zoom in a little bit so that you can see what the radius of this circle is. Let's see, the center is about here, and each one of these, the scale here appears to be 1, 2, 3, 4, 5. Each box is a 1. The radius of this circle is 1, 2, 3, 4, 5. And look at the 5s in my equation, here and here. The 3 and the 4 are the coordinates of the center of the circle. Let me just plot that point. Unlike algebraic expressions where you have x minus 3 tells you go to the right, in this equation you have a sine of t. This is actually 5 times the sine of t, now subtract 3. It would be different if it was the sine of the quantity t minus 3. Look what that does to the circle. So it's definitely not taking 3 from t and then taking the sine of that value. It's taking the sine just of t and then subtracting, multiplying that by 5 and then subtracting 3 from the whole thing. But that 3 and that 4, notice that it's a minus 3 and a minus 4. Those are the coordinates of the center of the circle. So you can tell what this is going to look like. It's going to be a circle with radius 5 whose center is at 3, 4. I think that's pretty cool. Anyway, a little bonus video. I hope you enjoyed it.